folks, if you're watching this. This is your stats lesson part 2. I'm going to try to make it not so long, but you are asking me to fit about 2/3 of a college level stats course into like a weekend. So I am doing my best. Today's lesson comes in 3 parts. Okay, part 1 of today's lesson is actually formulating your hypothesis in the correct manner. I realized I discussed this in passing briefly in the other video and kind of totally forgot about it, so here it goes. What the question you're actually trying to answer we call the alternative or the research hypothesis. Okay? And that states the question you're trying to answer, but we try to be as specific as possible. So for Morgan's experiment, I would say that the overall taste ratings of the cake samples according to the test subjects surveys, right? Because that's explaining how we're doing, where we're getting our numbers from. Differ, we can't say is greater or smaller because we don't know. We hope that some of them are higher ratings and some of them are lower ratings. So right now we're just going to say differ from the taste rating of the original recipe. So that's pretty good, but I'm also going to add due to the ingredient substitutions. So that is a pretty awesome alternative hypothesis. It says, well, we're expecting a difference between what and what, between the cake samples and the original recipe, and via what? Via the test subject surveys. And why? Because of ingredient substitutions. Excellent. So mutually exclusive to this is the null hypothesis, which is essentially the opposite. So we're going to say the taste ratings of the cake samples do not differ from that of the original cake recipe. Alright, this is a very critical step, even though it seems stupid, and I'll get to that in a minute. Okay, so the conditions of the alternative hypothesis we actually write as H sub 1. I'm going to try to enter in a sub 1. Aha! H sub 1. The null hypothesis, conversely, we write as H sub 0. Okay, so what our experiment is essentially trying to prove is that H sub 1, oops, S be capital, sub 1 does not equal H sub 0. Fantastic. That makes sense, right? We're trying to prove that these samples do have differences than the original cake. But mathematically, it's really hard to prove that something does not equal something else. It's much easier actually, it's much easier to test mathematically if H sub 1 equals H sub 0. Make sense? Oh, and this is usually written H sub 0 minus H sub 1 equals 0. That's mathematically and technically correct, the right way. Okay, now remember how earlier that I said the alternative hypothesis and the null hypothesis are mutually exclusive. We do this because if we can disprove this first guy, disprove minus h sub 1 equals 0, then we know that they're not equal. And that is why we made them mutually exclusive in the first place. Only one can be correct. So if one isn't correct, the other one has to be. So there's your logic for the day. And then if we know that they're not equal, we can support the alternative hypothesis. We have to run our tests though. We actually run all the tests, assuming that the alternative is equal to the null. My explanation is just, it's math. It's much easier to prove this guy false and then to prove this guy true. Part 2 is about power. You know, like gods and goddesses and feel my wrath. Actually, funny story. You know how there's an Egyptian god named Ra? There's like the sun god or whatever. Well, there's a symbol in Japanese that stands for Ra, like R-A, because they do syllables each symbol, and it kind of looks like a guy sitting on a throne. Look, can you see? The dictionaries are behind me. Oh my god, favorite shelf ever. Oh, guys, better watch out. She brought out the nerdy headphones. So power is the ability for a hypothesis test to reject the null hypothesis if in fact the null is false. Which sounds like a bunch of jargon, and you're right. It's just saying that the test does what it's supposed to do. So we like power. We like a lot of power. Now, the z-test I told you about is a test with a lot of power because you know the mean and you know the standard deviation. So you don't have to approximate anything, and your calculations are going to be pretty darn close and pretty darn correct, and your chance of making an error is going to be pretty small. So power high is high, chance of making an error is small. There's another test I want to tell you about. It's called the t-test, and this is what we have to use when we don't know standard deviation. And unfortunately, for your cake sample testing, we probably won't know standard deviation because we don't know what the actual population thinks about your cake samples. We only know what that sample size of 50 thinks about the cake. So I'm going to draw this out and show you how they're kind of related. Morgan, you'll remember from our lesson the other day that a z-score is equal to x minus mu all over standard deviation, which is the raw score minus the mean over standard deviation. For a z-test, you only have to change two small things. It's equal to z obtained, and obtained is the terminology we use for all the types of tests. And instead of just plain x for one score, it's x bar. In this case, x bar is the mean of the sample, and mu is the mean of the population. So to compare that to a t-test, I'll write out the t-test. Here's t obtained is equal to x bar over mu sub x bar all over the square root of sum of squares over n times n minus 1. So you'll see that there are several things that are the same about these two tests. The x bar is the same. Mu sub x bar you don't really have to worry about, just know that it's going to be the same thing. It's actually called the mean of the means, and it's mathematical stuff. So the really only thing that's different is the denominator. And what you're seeing here is just an approximation of standard deviation. So because we have to estimate something based on the sum of squares and n, which is the number of test subjects, we lose a little bit of power in this t-obtain test. But it still makes a very good approximation. So that was an independent samples t-test. That means when you test all your subjects independently. You, however, for your cake tasting experiment, did not do independent samples because you tested the same 50 people 7 times under each different condition. That actually is a good thing because it's going to increase our statistical power. A t-test for paired samples is the same thing as the t-test for independent samples, except for all the x's are replaced with d's, which stands for difference. So here we have t obtained equals d bar minus mu sub d bar all over the square root of sums of squares. Oh, looks like it's not going to fit, but trust me, it's the same thing. Sums of squared sub d over n times n minus 1. So those are 3 different types of basic tests. As you can see, they all look slightly similar. One only has a different approximation, and one has a different term used. I think I want to run a quick example of the paired t-test just to show you what it looks like. So here we have some lovely scientific data that I just made up off the top of my head. Right here we have a column for the original recipe, and next to it we have a column for the no egg recipe. In this example, we're only using 10 subjects. The first step I'm going to do is total both the columns. It's going to just be useful to have. Alright, next step is to create a difference column. And I'm going to just enter in the formula that I want the second score minus the first score. And I'm just going to put this for all the columns. And then I can also put the total for this column. And now I'm going to create the averages for each column also just by dividing by 10 because we have 10 subjects. The next column we're going to make is going to be d squared for the squared difference. And because this is Excel and I can make it do the math for me, I'm just going to plug in the formula and copy and paste. And now I can get a total for this column as well, and an average for this column, why not? Okay, so the formula for sums of squares, I realize I haven't shown that for you yet. Sums of squares is equal to the sum of x squared minus the sum of x squared all over n. So see if that doesn't confuse you a little bit. Before we go plugging stuff into the formulas, let's review what we do have. We have the total of the differences, which is the sum of d, is -6. We have the sum of d squared, which is 38. We have n, which is the number of participants, and that's 10. And then we have d bar, which is the average difference, and that's -0.6. To bring it all together now, the sums of squared for the difference is sums of squares sub d equals the sum of d squared minus the sum of d squared over n. And then we have the t obtained for paired samples, which is going to be d bar minus mu sub d bar over the square root of sums of squares of difference over n times n minus 1. And let's write down all the information we have. We have the sum of d squared is 38, sum of d is -6, n is 10, and d bar is -0.6. So sums of squares sub d is equal to 38 from our data over there minus -6 squared, which is 36, over 10, which is n, equals, let's see if I can do this in my head, 34.4? That looks about right. Okay, so now we can plug that, the sums of squares, into the t-obtain formula. So we have d bar, which is -0.6, minus mu sub d bar, don't worry about that, it's just always going to be 0, all over the square root of 34.4 divided by 10 times 990. And we're just going to plug in these numbers. We have -0.6 all over the square root of 0.38, and using my calculator, I get a result of negative 0.973. It's totally fine to have a negative number. That just means the difference was in the negative direction. So these scores are lower for the no egg cake than there was for the original recipe cake. Now, negative 0.973 is not a very extreme number, so chances are we would not be able to reject the null. I don't feel like looking up the actual data in the charts right now, but chances are we'd not be able to reject the null, and we'd have to conclude that there is no significant difference between the scores of the no egg cake and the scores of the original recipe. I'm such a good sister. Is it weird that I can only do that on one side, but I can't do it on this side?